Welcome back to our series on electricity and magnetism. In this episode, we're going to continue our exploration of electric potential. In this case, we're going to look at the potential from a point charge, a collection of point charges, and a charge distribution. First, a quick review of potential itself. Potential, which uses the symbol V, is a scalar quantity that is equal to the integral of the electric field along a path. We get to choose that path through the electric field, and the dot product of the path with the field will control the size of the potential. In the previous episode, we looked at equipotential surfaces, which is where there was a right angle between the electric field and ds. In this particular episode, we're going to look at instances where the movement is parallel to the field. That is, we're moving directly towards or away from the charge distribution. Okay, as I said, we have spent considerable time over the last few episodes looking at the electric field. And now that's going to begin to pay dividends for us, because if we want the potential from a point charge, we already know what the electric field of a point charge is. So I'm going to rewrite this as delta V because, of course, when we integrate with limits, we're going to find the change in potential from one location to another. And we'll put in those two limits eventually. That will be negative the integral. Let's substitute in the electric field for a point charge. That's going to be KQ divided by R squared. And of course, in this case, ds, the path, is actually going to be radial. We're going to move in or out, and therefore our path is going to be radial as well. So it will be dr. Because we're going to be moving parallel to the field lines, that is either towards the charge or away from it, the dot product just yields a simple product. It's either going to be positive when we move inward or negative when we move outward, but the limits of integration are going to take care of that for us. Well, this becomes a pretty easy integral to apply. I can now say, well, the negative is taken care of by the integral, and this is just going to be KQ over R between the two limits. And now is time to talk about what the limits of integration should look like. As I indicated in the last episode, potential is analogous to altitude for potential energy for gravity. As I lift an object away from the Earth's surface, its altitude increases. And as I move a charged particle away from another charged particle, I should see the same increase or decrease of potential as a result. Of course, if I move a positive charge towards another positive charge, I know it will increase in potential energy. The difference between these two analogies is that mass always attracts other mass, but charged particles sometimes attract and sometimes repel. A negative charged particle would experience a very different potential change than a positive charged particle would. So we have to take that into account in looking at how potential is going to be defined over distance. What we've agreed upon is basically this. If potential is an indication of the curvature of space that the electric field creates, then we want zero potential to be where space is flat. It's that is, it's no longer curved. And for charged particles, that will only occur at an infinite distance. If we get far enough away from a charged particle, space will no longer be bent as a result of its presence. And so we will consider infinity to be the location where the altitude is zero, the location where the potential is zero. So we want to measure this from infinity to our final location, which will be some radius away from the charged particle. So the limits we select is this. We want to go from R to infinity. So those become our initial and final positions. And of course, if we substitute those both into this relationship, we're going to get KQ over R minus 0. Because the infinity in the denominator is going to create zero potential. Therefore, the change in potential is the change from 0 to whatever our secondary quantity is, and that becomes the final voltage. V is equal to KQ over R, and it's always in a radial direction, so we put the R hat vector to indicate that. This is the potential for a point charge. If we want to calculate the potential, we simply insert the charge. Positive charges would have positive potentials. Negative charges would have negative potentials, and it's sort of an indication of the altitude of the curved space that's created as a result of the central charge. Of course, it's inverse R, which means the potential increases or decreases in magnitude much less quickly than the electric field does. The electric field is a function of 1 over r squared for point charges, and of course the potential would just be 1 over r. So the altitude changes less quickly than the magnitude of the field. Well, if this finds the potential for a single point charge, what if we have multiple point charges? Well, in that case, because potential is a scalar quantity, we simply sum them. So if I had a collection of positive and negative charges that were all in a region, and I wanted to know the potential at some point within that region, all I need to be able to do is find the potential contribution of each one. That is, the potential in this distribution would be the summation over I of k qi over ri. Because there's no vector relationship with potential, I don't have to take into account the trigonometry of the angles from which all these charges contribute to the potential. This is just a simple sum. Now, what is complex is each one of these would curve space in a different way. It would indicate a different elevation of their curvature. But at this location, all three of those curvatures are going to sum to a single scalar altitude. That's what this will indicate. So potential is much easier to calculate than electric field was because we simply don't have to take into account its vector nature. It's possible for potential to be positive or negative, so sometimes they will add to each other or subtract from each other, but that's natural behavior for all scalars. Well, the next natural turn then would be, well, what happens if the charge distribution becomes continuous? What if we go again to some sort of a linear charge distribution like lambda along a line, and I want to figure out what's the potential at this location? Well, in a similar way to what we did to find electric field from a charge distribution, we can find potential. That is, dV, the individual little element right here, would have a charge of dq at a radius of r, and we would be integrating it over some dx. So what we would want to do is take k dq, except this time just over r rather than r squared. And then if I could find dq and r for the given distribution, I could go ahead and integrate both sides, and I could find the voltage from any charge distribution whose geometry I could exploit. Because we did this similar process to find electric field, there's really no difference here. The only difference is the dramatic simplification of this being a scalar process. When this was electric field, we had to take into account that each electric field contribution might point in a different direction. So we had to work out what the vector integration was to produce the overall direction and magnitude of the electric field. Of course, we don't have to do that here because the contribution of this dq will either increase or decrease the altitude at v, and every other one will have an equivalent impact on it. Therefore, all we have to do is complete this integral. Its scalar completion will provide the altitude at that point, and I don't have to take any vector consideration into account. Now, of course, you'll recall that this process was arduous, and we only went through it because it provided a good context for the concept of flux and for determining electric field through Gauss's law. So let me direct you back to our initial definition for voltage, which is it's negative the integral of E dot ds, where ds is the path. That, in my mind, is a far superior way to actually determine what the voltage is at any point in a uniform charge distribution. And the reason why is we spent a lot of time calculating the electric field from all these different distributions, and now we can reap the benefits of our labor. If we know the solution to what the electric field is as a function of distance, then we simply have to dot that with our intended path, putting in reasonable limits of integration, and we could solve for the voltage directly rather than going back to the source and reintegrating potentially a problem that we've already integrated before. So keep that in mind. Certainly for problems of continuous charge distribution, you can always calculate the voltage from scratch. But if it's a distribution whose electric field is already known, this would be a far superior method of approach.